Hello, y'all. Darrell Berry Jr. here, back with some working out some quantum problems. So these are some problems that I'm in the process of working out. So it'll be a bit detailed. Let me raise this a bit. So I'll just jump right into it, have a new screen layout to see things a bit more fully on the pad. And we'll go from there. The sound seems okay. If you find any issue with it, let me know. And I can make adjustments. Be sure to drop a line if you're watching. All right, so let's go ahead on. So the first one is going to be about energy levels of an atom, which historically I've needed some help with. Right? So we have a hydrogen atom, N equals 4. And I'll probably do this in 2 parts, by the way. I'll take a break in a bit and come back. So first we need to take in, I'll get all of the degeneracies. So if N equals 4, I'm actually bring up my notes. I also have to remember the details of this. Actually, let me see if I can work it out. So if N equals 4, L equals 0 to N minus 1. So L equals 0, L equals 1, L equals 2, and L equals 3. And ML equals negative L and everything in the middle to L. So L equals 0, and L equals 0, L equals 1, ML equals negative 1, 0, 1. I'll write this slightly differently. L equals 2, ML equals negative 2, negative 1, 0, 1, 2, and L equals 3, ML equals negative 3, negative 2, negative 1, 0, 1, 2, and 3. So the MLs, we can count these for degeneracies. So this is 1, 1, plus 3, plus 5, plus 7 equals 16. But each of them has a spin. So 32 is the total degeneracy. And let's work this out. So we're going to take into account the electron spin only. So spin is always going to be 1/2. So if I get the j, that'll be L plus S greater than 0. So the j for this one is negative 1/2, 1/2. The j for this one for ml equals 1. That's not going to give me anything for the negative. For ml equals 0, j equals 1/2. These for excuse me, not mll. Thinking about that incorrectly. I'm going to get the j and the mj. So j is L plus S. Or I guess I should say plus minus greater than 0. So if ml equals 0, j equals 1/2. If ml, excuse me, if L equals negative 1, there is no j. If L equals 0, j equals 1/2. And if L equals 1, j equals 1/2 and 3/2. So we have 1, 2, 3. I can actually move these up a bit. If L equals negative 2 or negative 1, it'll be negative, so that doesn't count. If L equals 0, j equals 1/2. If L equals 1, j still equals 1/2 and 3/2. If L equals 2, j equals 3/2 and 5/2. And check and see, like I said, I'm working these out, so I have to check and see if I'm adding these up right afterwards. So again, the negatives won't do anything. L equals 0, j equals 1/2, L equals 1, j equals 1/2, 3/2. L equals 2, j equals 3/2, 5/2. L equals 3, j equals 5/2, 7/2. So 1, 2, 3, 1, 2. Let me see, this right underneath it. 1, 1, 2, 1, 2, 2, 1, 2, 3, 2, 2, 4, 6, 8, 10, 12, 13, 14, 15, 16. And each of these j's will have an mj. It's plus or minus. So mj is plus minus 1/2. Mj plus minus 1/2. Mj plus minus 1/2 plus minus 3/2. Mj plus minus 1/2. Mj plus minus 1/2 plus minus 3/2. Mj plus minus 3/2 plus minus 5/2. And these will all be the same here. except I'll also have a mj equals plus minus 5/2 and mj and plus minus 7/2. So that should give us the 32 degeneracy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 21, 2, 3, 4, 5, 6, 7, 8, 9, 33, 132. So we confirm that there's a degeneracy of 32. All of these different configurations with the same energy. We could either take the L's times 2. So the L's times 2 will give the degeneracy. Or we can count up the MLs, excuse me, the MJs. So the number of MJs is the same thing as the L states times 2. And the L states, if I haven't covered it on this channel, is basically the shape of the orbital of the electron, for instance. So L equals 0 will be S, which would be spherical. L equals 1 will be P, which is this sort of uh, lobe. L equals 2 will be 4 lobes. And L equals 3 will be 8 lobes. So you have all of them spread out in such a way as to uh, balance out the electric repulsion. And there we go. Let's see what the next thing is. So got the degeneracy. So technically J is degeneracies. Excuse me, L times 2 are the degeneracies. And these are the allowed values of J's. Let me check my answer here. Right? Everything seems okay. And so apparently this tells us the sublevels this breaks into. Let me check one more thing here. So L is the orbital angular momentum with the ML magnetic quantum number. Oh, and by the way, this is the ML number of ml times 2. Got the J's. And apparently, so I'm still not clear on how many sublevels they split into. So I'll ask that in office hours today. This method does give me the degeneracy for sure. I think there's a detail I might be missing. All right, so we'll move on. So this question is about if a particle in a two-dimensional square box. So basically our psi is psi of xy, which by default will be psi in x, psi in y, are the default equations. And right now we want the infinite well. You can imagine this is our box. These are the walls of the box with infinite potential on the outside. And our particle is inside this box. If we were to draw axes, we'll call this X and this Y. All right. And we can say that there's a potential perturbation. You know what happens with this sometimes? Some reason of the bias, consider the first excited states, which in the absence of the perturbation is degenerate. So the first degenerate excited state is going to be n x and y equals 1, 2, or 2, 1. So technically this would be psi nx ny, or nx comma ny. And those are the nx's and ny's we need. So let's say I have the box that I have drawn up there, but it is perturbed by 1, 2, 4, 5, 6, 7. 1, 2, 4, 5, 6, 7. Okay, square box. And actually, I want to make it a little bit bigger. 1, 2, 3, 4, 5, 6, 7, 8. And let's say that is that like a third of the box? So it doesn't necessarily matter. I'll make it one more bigger. And let's say a third of the box. To the perturbation. So we're looking at this. And this is the perturbation of V naught. In the center of the box. And I'm not drawing it precisely because I think I want to actually calculate it as well. We need, for which of these perturbations will the W matrix be diagonal? So the default wave function will look like this. So basically, these have to be separate. We know that if n equals 1, that's just a wave function with no node. If n equals 2, that's a wave function with one node. So if we have one going along the x and one going along the y, then we have to have either n x equals 1, and let me actually reposition my axes. And I'll let x be how we normally think of x and y be how we normally think of y. And this is the origin. So now we have x, y, origin. So if x is 1, so we have 1, 2. X is going to have no node, and y is going to have one node. So y will look like this, and x will look like this. So there will be one node in the middle along y. Nothing will be there. And it's kind of difficult to write, but technically the blue one will be the entire box. It'll be like a hill over the entire box. Whereas the Y one would go up here and go down on the other side. And for n equals 2, y equals 1, it would be the same thing. Where now y would fill up the full box, and x will have one part coming over, one part coming under, a node in the middle. So it'll look like this. So if we were to look at the way this interacts with this perturbation, like this, for the first one, is this symmetric over the diagonal? So if I draw a diagonal here and flip it in that way, it looks like it'll be different. Let's affect it. Let's see. The perturbation matrix is Wij equals psi I, the perturbation psi j, and apparently if psi 2 1, psi 1 2 equals 0, then the diagonal does not mix. The perturbation does not mix the two basis states. So as long as that's 0, or long as either of these are 0, which is basically the same thing, then we can say it's diagonal. And it happens when there's symmetries. So the way these wave functions work, psi ij equals psi in x, psi in y, xy. So that equals square root 2 over a sine in x pi x over a, square root of 2 over a sine n pi x over n pi y over a. So these are the default wave functions. There's one for x, one for y. So psi 1 2 equals psi and x equals 1, psi and y equals 2. Root of 2 over a sine pi x over a, root of 2 over a cosine, sine 2 pi y over a. And the reverse is true for the other scenario. So we have 2, 1. And we have this. So these are the two equations that we're working with. And I may actually work these explicitly. So we're going to test the diagonals on this. Psi 2, 1 star, psi 1, 2. That's going to be psi 2, 1, psi 1, 2. That's going to be 2 over a sine 2 pi x over a sine 2 pi y over a 2 over a sine pi x over a sine 2 pi y over a. And this will be the perturbation matrix. Well, if I was to multiply in uh, the perturbation. So if I was to simplify this, we have 4 over a squared sine pi x over a sine 2 pi x over a sine pi y over a sine 2 pi y over a. So on the diagonal, it looks like there's definitely symmetry on either side if I flip it. So perturbation about the diagonal should be 0. But let's go ahead and test this and confirm it. So we basically have just copy this down. And we'll integrate over the perturbation because this is 0 everywhere else. And I set this for a third. So this is a over 3 to a over 3. I think we have to do the identity thing. So, oh, and this will be, we put the bounds a over 3, a over 3, 2a over 3, 2a over. I wonder if I can do this with a calculator. Mm, I don't know why I remember seeing an integration thing here before. All right, let me just look up the identity. So this is the product of sum identity. So sine A sine B equals 1/2 cosine A minus B minus cosine A plus B. Useful whenever there is a sine or cosine or double. I don't know what the uh, cosine version would be. And let me check just in case with integrals on a T84. Oh, I see. Right, gives me 0. Hey, what's going on, Canal? I am having a good day, actually. Thank you for asking. And hopefully you're doing okay. I did this integral just now and got that it was 0 in the calculator. So I do feel tempted to actually try it out and see what happens. So let's take a look and see if we can confirm this with some practice. But at least I know how to do it in the calculator. So apparently all you have to do is click math and 9 on a TI-84. Yeah, you can do the math button and then you can do 9, which is, I guess that's function integration. And then this will actually give you the definite integral to plug in. So simple enough. So, and let me know if you have any questions on anything. So I'll do integral a over 3 to a over 3. And I should be able to separate these integrals since they're not. Oh, hold up. Just the separation. Yeah, because the V naught just comes to the outside. I should be able to do these separately like this. So we would have V naught. Why don't we do just one of them? They're the same integral. So we would have integral a over 3 to a over 3, 1/2 cosine pi x over a minus 2 pi x over a dx minus 1/2 a over 3 to a over 3 cosine pi x over a plus 2 pi x over a. Doing just the x one, because it's the same integral. So we'll have 1/2 over the whole thing. That'll be sine of negative pi x over a. And dividing by the derivative, that's negative a over pi minus sine 3 pi x over a. Divide by the derivative, that's a over 3 pi. And that's 2a over 3 to a over 3. So we've also plugged this in. We have 1/2. And actually I can make this negative 1/2, put that on the outside. Then we'll have a over pi sine of, so the a will cancel. It'll be negative 2 pi over 3 minus plus a over 3 pi, since I took the negative out, sine. So this time the a will cancel and the 3 will cancel. 2 pi minus, since I took the negative out, plus the negative of the second half, a over pi sine negative pi over 3 plus a over 3 pi sine, and a will cancel, 3 will cancel. So that would be just pi. If I made any errors, let me know. I could actually delete this. So let's see what these values are. So we know that sine of any n pi is 0. And so now we have -1/2. So sine of 2 pi over 3. I'll just put this in the calculator. That's a over pi negative 0.866 plus a over pi of sine of negative pi over 3 negative 0.866. Maybe I did something wrong on one of the calculations. Plus, I took this negative out. I made everything on the inside plus. The negative is still on the outside. So that's what I did wrong. So this will still be subtracted because I took the negative out. So this will be minus. So this is the first half. And this is the second half, which is subtracted. And the whole thing is times a -1/2, which is outside the entire process after it's finished. And that does in fact equal -1/2 times 0, which is 0. And of course, we know the other one is going to be the same because it's the same integral. Now I'll bookmark this where I found the way to do that. Why does this happen? Maybe I need to uh there's some new time setting that they added to this thing or something. I'll check on that really fast. Uh, oh, I'll do it later. You just may have to deal with me having to re-initialize this thing periodically. Okay, so we see that this one here, the W matrix is 0. So that means that it's symmetric over the diagonal. Wij equals psi ij psi ji equals 0. Thus symmetric over diagonal. And of course, we can tell by looking. All right, it's been just over an hour. I'll go ahead and take a break, and I'll be back to continue with this problem with other symmetries. So I'll do basically I'll also copy these down. So I'll try this symmetry. We have a third walled off that way. I'll try this symmetry. Where the middle here is blocked off, but it's a bit like this. And I'll also do one where the perturbation is like this. All right. So for me, between 15 and 30 minutes, I'll be back. I will continue with some more quantum 2 problems.